Okay, Bismillahirrahmanirrahim. Just a few administrative things. So yeah, you know that Shahwal has changed. The announcement was for the other people. They are not here because they went to the wrong Shahwal. So there's no point making this announcement. I'll be assigning a homework today, inshallah. It will be on the LMS website. The LMS website is up. All of you should have been able to access it. If you have not been able to access it, then you have to give me your email address, because other than one email address, I think it was mistyped, it didn't have enough characters in it. Other than one, I added all of them. So anybody who is not on the LMS website, they should let me know so that I add them there, because the slides are already there. We haven't been able to get the recording fully yet, but that will soon be uploaded there also. The homework will also be there, and you will be submitting the homework there, so it's important that everyone is on the LMS website. Also, I made a WhatsApp group, so what you need to do is I'll just write it here, okay? So that's the WhatsApp group invite. If you want to get added to that, it's your choice. Okay. What else? The homework will be assigned today. It will be due on Tuesday. So you have to. Any questions? Administrative issues? Everyone is doing okay?
Sir, the voice was
Samme? Okay. All right. Okay. So, any other issues? Any questions regarding previous lecture? Okay. So, what did we do in the previous lecture? We started off our treatment of 2D primitives, which is points and lines. We just talked about two primitives. We didn't talk about curves, circles, connects, and so on. We'll pen that if we need to talk about those, we will. But essentially, we are talking about points and lines right now in this course. And then we talked about interaction of points and lines in this new P2 space, P2 type of representation. What sort of equation I have to verify a point lies on a line. The point formed by the intersection of two lines, how do I compute that? By cross product. How do I find the line joining two points, again by cross product, and so on. Okay, so we discussed all of that yesterday, and in fact we came to the conclusion by developing this mathematics that in projective geometry or in projective algebra, the points and lines are equivalent in their representation. They look, as far as their representation is concerned, their mathematical representation is concerned, they are exactly the same. Okay, and therefore we talk about this duality concept that if I draw a point on a plane, I can have a dual space, another plane, dual to this plane in which this point will be a line, and every line will be a point in that space. Okay, so if two lines are intersecting at a point in the original space, in the dual space, those two lines will be actually points, and that point of intersection will be a line joining those two. Okay, that's the duality theorem. Yeah.
Sir, when you're talking about duality, what if the points and the lines are on the same plane? How do you differentiate between a point and a line? Like, you know, the representations say, I don't know the representations.
Yeah, we just have to know. We just have to know. As far as their mathematics is concerned, they are treated exactly the same. Right? Both of them are a three-dimensional vector in homogeneous coordinates with the same equivalence classes, and 0, 0, 0 is not defined for each of them. So it's exactly the same. Alright? Okay, So I want to, okay, by the way, in just administrative announcements, I said here's the WhatsApp URL. The LMS website is up. You should visit it every day because there will be new content posted with each lecture. Today there will be a tutorial. I think it is in 304. You should check your schedule. It's either here or here. Okay, and in the tutorial, what I want to do is I want to cover some review of linear algebra. Okay, because we'll be talking a lot about different linear algebra techniques in this course. So I want to just review them in one go, so you make sure that you understand those concepts. Concepts like vector spaces, what's the rank of a matrix, what's the null space, how do you do SVD decomposition, what does it really mean, what is meant by an orthonormal matrix, and so on. Okay, these are things that all of you have seen in linear algebra. These are basic concepts in linear algebra. Other than SVD, sometimes people skip it in a course. But the rest are just basic concepts, but it's good to revise them because we'll be talking about them on the fly in this course, so it's good to revise them. Also, I'll briefly go over the homework problems so you know what's required for it. Okay? So I recommend this will be at 2 o'clock, I think in that room. Alright, so let me begin today by talking about two-dimensional transformations. Transformations on the 2D plane. Okay? Again, this is something that you have seen before in linear algebra, or maybe even in high school. There are topics of 2D transformations in high school, but I just want to go over them and make sure that we build the base that we need to talk about images and information. Okay. Oops. Okay, so what is a 2D transformation? A 2D transformation, I've defined it, it's a mapping from one 2D coordinate system to another 2D coordinate system. Okay, so it's a 2D, when I say a 2D transformation, what I really mean is a 2D to 2D transformation. The reason I'm emphasizing that is because in this course we'll also talk about 3D to 3D transformations, which are transformations in this world. And we will also talk about 3D to 2D transformations, which are really which is what a camera is. Okay? And we will talk about 2D to 3D transformation, which is a structure problem, recovering the 3D structure from an image. Okay? So a 2D transformation is also called a spatial transformation, a geometric transformation, or a warping. And one of the so first, before I talk about transformations, I want to motivate you about why we are talking about these transformations. And one of the problems in which this transformation comes in handy is the image registration problem. So image registration is the problem of, it's the process of transforming two images so that the same features overlap. Okay, so here's an example. So I have, so this is a data set from, let's say, a UAV or even a satellite, maybe. So there is one image, let's say from a satellite or a high altitude aircraft, which covers a very large area. Okay, and that's this image. I call it the reference image. Okay, it's covering a large area. You see a runway here and some structures and so on. And then you have some low-flying aircraft like a UAV that has a video camera on it, so it's taking a lot of images. Okay, now these images are only a small portion of that large image. Okay, so what is required is that I want to find this image in that large image. And why would I want to do that? So for example, I mean there are many reasons. But for example, have you heard about the Tomahawk cruise missile, right? Or Pakistan also has a version, Babar cruise missile. So you understand what's a cruise missile? So there are ballistic missiles. Ballistic missiles you fire, they go in a trajectory and they fall, right? And there are cruise missiles which fly like an aircraft. They can turn and right. So that's why they're called cruise, because they have wings and they can kind of like fly. So one of the mechanisms that is used in cruise missiles is that you want to know your location accurately, because let's say the missile is going to fly 1,000 kilometers and then it needs to hit its target. if you are not navigating accurately, then maintaining positional accuracy over a 1,000-kilometer flight is actually a very difficult problem. So, so what happens is that, of course, you can use GPS, right? But GPS signal is a weak signal. It's coming from faraway satellites, so it's a weak signal. And so it's very easy to interfere with. If I don't want myself to be hit with a cruise missile, I can just generate interference on the GPS channels. Okay, and that's easy because my transmitter will be close by, so it will be much more powerful than the signal coming from the satellite. So I'll just distort the SNR and so in mission critical scenarios, you don't want to rely on ABS in this type of scenario because your adversary can kind of affect it. So one of the mechanisms that is used there are actually multiple mechanisms which is used, but one of the mechanisms which is used there is this, that the aircraft, the UAV, the missile, takes a picture and then very quickly registers that picture in a large scene that is already stored on board. And where you find the match, you say, oh, therefore I must be here from your camera. Okay, so that's one of the mechanisms which is used in these devices.
Maybe for towards the bottom left image.
Yeah.
That could be multiple places on the map.
Yeah. So there are lots of issues, but I'm saying it's done this way. Practically, it's done this way. So yes, you have a good point. This image could map on multiple images on the map. But what happens is that one of the things that they use is that they take one image and find position from there. And that position surface, I mean, it matches here and here and here, it matches at 3 locations. But then they go forward and match again. And then maybe this one matches there, and there, right? And then next one. And then they say, well, all of them are consistently matching at this location with the offset of my flight path. And therefore, this must be the correct location. And it just makes it very, very robust. That's one of the strategies which is used. There are, in the current systems, as far as I know, at least there are 3 modalities. No, at least there are 4 modalities which are used for calculating position. And then there is a Kalman filter type of strategy to integrate them together. I mean, a sensor fusion strategy to come up with one positional estimate for the bird. Okay. All right. So I'm just motivating you for why we need to study transformations, so that you don't believe me that we are just doing mathematics for nothing. So let's say this is the image. This is my mission image. I took it while on the mission, and this is the previously stored image. So the process of image registration is I want to find a transformation that will say where this is in this whole thing. Like in this case, it's about here. Okay. But you notice that the modality of this image, I mean the colors, the contrast, and so on, is very different from the modalities of this image. Because this was a low resolution video camera which was taking this picture, and this was a kind of like a satellite sensor or a high resolution sensor. So you have differences in modality. Here I'm showing you what you get as a result. So here I've overlaid one of the images on the portion of the background. You notice that it's not just a simple translation, which is, there's a bit of like distortion this way because the image was from some angle. But you notice that this is correct registration because you see continuity of features. Okay, so we have found the transformation correctly, whatever was the transformation to do the mapping. So what is it, the transformation here? It's a mapping of one coordinate system to the other. In this case, the coordinate system of that original image and the coordinate system of the reference image. I'm finding the mapping between them. Yeah.
So could this be used for increasing the resolution of satellite images?
Yes. It's actually used for that. So when you are doing field service, let's say for crop monitoring, so you might fly an aircraft over a portion of an area and get very high resolution imagery because you are low in height, then augmented with satellite imagery over a large area. So it could be used in a number of different scenarios. So here are some more examples, right? This one. Now you notice the mission image was partly cloudy. So that's another problem that you need to deal with, that it should still work, but it worked well, right? This was the actual mission image. I'm just showing you how degradation of quality it was. Here we are showing you in 2 different colors overlapping, so you can judge the quality of registration. And then of course you are on a flight path. So if if you are registering each one of those images correctly, you will get like a continuous flight path in which there will be continuity of features, like the runway here, right? And so that's what you are saying. This portion of the satellite imagery now stands updated. The satellite imagery might be 2 years old, but this portion now is current because you flew a mission. So this is a very important problem for drones, UAVs, field surveys, agriculture. I mean, lots of applications, even other than trying to kill people. Yeah.
But sir, I cannot see the practicality about this, because since the image would be like in megabytes, I suppose.
Yeah.
Like since it's a very high resolution image, so by the time the picture uploads, the plane uploads that picture, तो तब तक वो ये खराब नहीं हो जाएगा कि वो अगली लोकेशन पे पहुंच
No, so this is done in real time on board. So when you fly the mission, you upload the imagery. So for example, I know for the US Tomahawk cruise missile, when they plan a new mission, they prepare imagery for that mission. So they say, okay, we want to hit a target in this location. So they prepare imagery for that mission. And at least in the previous systems, I don't know about now, but at least in the previous systems, that preparation process was several tens of hours, maybe 80 hours of preparation time was needed in the Block 1, Block 2 system. Okay, so they would do a lot of preparation and then upload that imagery along with a lot of other things into the actual device. And then all the processing of the mission images is happening real time. It's not being beaten back or done like that. Okay. So there is a lot of hardware which is put into the bird for real-time processing, and the algorithms are very important that do this real-time processing because speed is a lot of concern. You want real-time performance. You don't want the answer to come back after 2 minutes because the position of the bird has already changed. So there is a strong constraint on performance side here. Yeah. There was a question there.
तो पहले वो सारी इंफॉर्मेशन उससे कंपेयर करता है जब वो मिसाइल एक्चुअली फ्लाई करती है अपनी लोकेशन
You define some target area. You upload imagery of that target area into the bird. You also do other things because there are other modalities. There is a modality which is called TERCOM, which matches terrain signal. I mean the 3D height. So they upload that imagery also. They actually plan where they are going to do the matches. So they upload those portions of the images, and that planning is based on where they will potentially target. So that because once you do this matching, after that if you stop doing this matching, your error will continue to increase from that point onwards. So there is a lot of considerations done in that mission planning phase.
So does the bird itself explode with the missile or does it sort of?
Okay, this is not the ballistics course.
But if it was to explode, then the heavy machinery inside the bird could explode as well.
No, so it's all gone. I mean, all the hardware you put in the bird is one use, single use hardware.
I could see this as used for drones, which
Yeah, drones you reuse it, but in a cruise missile it's all gone. So, but that's the idea. Okay, this is a more peaceful application of the same thing. Medical image registration. So here you have two different modalities, maybe a CT scan and an MRI, right? Or a CT scan taken at two different times, because in, let's say, a cancer, one of the critical parameters is doubling time. How fast is this cancer growing? So you do a CT scan now and maybe a CT scan after 15 days or 1 month, according to whatever the diagnosis the doctor has. And then in between those scans, they want to find out how fast it's growing. So they have a parameter which is called doubling time, right? Or between an MRI and a CT scan and so on. So in that case, what is required? I have one image and I have another image, and to be able to do this measurement, I first need to register them so that the common areas overlap. Then the differences will be highlighted. Okay, between them. Sometimes we register with a standard atlas image, which is a sort of drawing in so that the image comes in a standard configuration, and I can do measurements. This feature is bigger than what it was supposed to be. Like let's say the spleen. The spleen is enlarged. You want to measure that. Okay. The same kind of transformations are used in what you are familiar with in making panoramas, right? So now this used to be like fancy algorithms till a few years back, but now they are available in every phone. You take a picture, another picture, another picture, another picture, and your camera automatically stitches them together to create like a nice panoramic view, right? Hopefully we'll do a homework on this. So how is that done? You register these images together. The first picture and the second picture have some overlap between them, and in that overlap you figure out, okay, exactly what's the transformation that makes them overlap, so that I can transform the second image and put it on the first image, and so it becomes like an extended image, and I keep doing that for a number of images, okay? And all this processing is done on the processor of the phone itself. This is a very interesting panorama. So this was done through a drone photography over Manhattan. Another picture. You have these types of cameras which give you 360-degree views now, right? Panoramic views. And this is a product by Point Grey, which is now bought by Fleur, so it's actually a product by Fleur now. They have like 1, 2, 3, 4 cameras, 5 cameras actually on this, and then one more on top. And then so each of the cameras is taking video as you are moving, but then they fuse them together according to the correct transformations. They fuse them together into like a view like this. Okay. So yeah. Okay. So 2D transformations then are very important. Each of the examples that I showed you is a 2D to 2D transformation, two-dimensional transformation. So the basic operation in 2D transformations, let's see how they are done. So the basic operation in a 2D transformation is matrix multiplication. That's it. The point to be transformed, let me call it xy. The point after transformation, let me call it x prime, y prime. I'm writing now in inhomogeneous coordinate. Like I said, for convenience, I'll keep switching between them wherever for simplification. Okay. So the basic transformation is done like this. You have a transformation matrix applied to the coordinates of the point. Let's say this point is at 10, 20. Okay. So I apply a multiplicative transform to it. This 2 by 2 matrix here, so it becomes this, and I say that's the new point. So this has now shifted to another location according to this transformation. Okay. And the methodology here is that I keep the transformation matrix the same and keep switching these pixels. I do this for the first pixel, the second pixel, the third pixel, and so on. I do this for all the pixels, so all the pixels get transformed consistently by this transformation matrix. Okay, so here's an example. Yeah.
Are we given this transformation matrix, or do we use some matrix?
It depends on the problem. So if the problem is okay, transform this image by this rotation, so you will be given the transformation, right? But in the registration problem, we have to estimate that matrix. What's the correct matrix so that these two images will align together? Okay. So here's an example. This is an image. I put 0, 0 here at the top left corner. This is, let's say, A0, AA, 0A. These are coordinates. Notice Y is going this way, X is going this way. And I get this as the transformation matrix. Let's say the transformation matrix is 0.5, 0, 0, 0.5. So what will happen? I will take the first point, let's say I take 0, 0, and I multiply this with this matrix, and I figure out what do I get? 0, 0. So that means this point will stay here. Under this transformation, it's not going to move. Then I take the second point, let's say A0, and I multiply this with this. I realize that it becomes 0.58, which means this point is going to move like halfway here. Okay? And then I take the third point, let's say AA, and I realize that it goes to 0.58, which means it moves here. And you see the pattern now, right? So I could do this for some other point. Let's say I took the original half point here, then it will go to 0.25, 0.258. So by doing a few examples, I don't have to do it for every point just to build a picture in my mind. For a few examples, I realize what sort of transformation is happening here, which you can see that it's like a shrinking transform. Yeah.
So normally for images, do we take the coordinates and then transform them, or is after state pattern which is only us?
We'll come to this. We'll come to this of how you actually work. Okay. So what would this transformation do then? Yeah.
So x coordinate 1.5 times हो जाएगा.
X coordinate will expand and y coordinate will shrink. Yeah. So you kind of get the sense that if the matrix is like this and there is a 0, 0 here, then this is a scaling along x and this is a scaling along y. Okay. So in general, the scaling, which is a zoom or an unzoom type of transformation, looks like this. There's a factor sx, sy, 0, 0. Okay? Alright, what about this transformation? What would this do? Okay, so you don't have to do it in your mind. You can just take a few points, apply it, and then you will kind of realize what this does. So let me try to apply it on this image, right? So I take 0, 0, it stays at 0, 0. I take 1, 0, 1, 0, it stays at 1, 0, right? But when I take 0, 1, it actually becomes 1, 1, 0, 1. So 1 times 0, 1. So 1 times 0 plus 1 times 1, that becomes 1. And 0 times 0 plus 1 times 1, so that becomes 1. So 0, 1 becomes 1, 1. Okay? So that comes here, and this 1, 1 actually goes to 2, 1. Okay? So we call this a shear transformation. It's like if I had a deck of playing cards and I kind of like slide them like this, right? So it's a shearing transformation. In general, a shear in the x direction looks like 1 E 0 1, okay, where E is the shear factor. And I'm calling it a shear in x direction because what I drew, remember the x direction was like this. So what I drew was actually a shear in x direction. Okay? What would a shear in y direction look like? The scale factor would shift from here to here. Now the y coordinate is being impacted. Okay? So it becomes x coordinate remains the same. When you are shearing in y direction, x coordinates remains the same, but y coordinate gets changed in proportion to the x coordinate. The bigger your x is, the bigger the y will go. Okay? So that's a shearing in x direction. If these seem like not so obvious to you, I recommend that you do some practice, and it's actually straightforward. It's straightforward matrix multiplication. In fact, matrix multiplication can be thought of as just transformations. Okay, so let's talk about rotation. Rotation is a bit more involved, but let's try what would be a rotation, okay, from scratch. And I'm sure you might have seen this somewhere before, but let's just review. Okay. So what's the goal here? I have a point x1, y1, and I want to rotate it. When I say I want to rotate it, I have to define first what is the point about which the rotation will happen. What is the center of rotation? So in this case, I assume that the center of rotation is origin. Not only do I have to specify the center of rotation, I also have to specify how many degrees I want to rotate and in which direction. Here on the 2D plane, I can have two directions of rotation, clockwise or anti-clockwise. Okay, so the matrix will change if any of those things changes. So let me say the angle of rotation is theta in general, because I want to derive a general matrix. But I will always consider counterclockwise, anti-clockwise rotation as positive angle. Okay, that's just by convention. So we are making two conventions here, which are commonly used. One, that the rotation happens about origin. That's a simplification. We'll talk about relaxing it later. And second, that the rotation happens, if you give me a positive angle rotation by 45 degrees, that would mean counterclockwise. Okay. Clockwise would be rotation by negative 45 degrees or rotation by 315 degrees. Okay. All right. So now my task is, given that I have defined this convention, my task is I want to relate x1, y1 to x2, y2. If I'm able to do that, the matrix that does that relationship will be my relation matrix. Okay. So let me define a new angle here, phi, which is the angle that the original point makes with the x-axis. Okay. This is just for derivation. I realize that this length is not going to change because it's a pure rotation. So this length must not change. Rotation preserves lengths. Okay. So I write what this length is here, and I write what this length. That's the strategy. I'll write what this length is and what this length is, and in terms of my input parameters, and then try to make a relationship between them. So what is this then? This is r cos of phi. Okay. It's x1, but it's r cos of phi in terms of those parameters. And what is this length? This is y1, which is r sine of phi. Yeah, agreed? Everyone agrees with that? And then, so what is x2? Well, that's the only thing that has changed is the angle, and the angle is theta plus phi now. So x2 is r cosine of theta plus phi, y2 is r sine of theta. So now I can take x2 and I can expand it by the double angle identity. So cos of a plus b is cos a cos b minus sin a sin b, right? So it's r cos of theta r cos of phi minus r sin of theta r sin of phi. That's what x2 is. And y2 is r sin of theta cosine of phi plus r cosine of theta sin of phi. That's why the sine, the double angle identity for cosine and sine. Okay? So I have x2 and y2. I wanted to relate, what did I want to do? I wanted to relate x2 and y2 with x1 and y1. So I realized that r cosine of phi is nothing but x1 and r sine of phi is nothing but y1. So I can do that substitution. So x2 becomes x1 cosine of theta minus y1 sine of theta. And y2 becomes x1 sine of theta because r cosine of phi is x1. So x1 sine of theta plus y1 cosine of theta. Right? And that's what I really wanted. Because I wanted a relationship between x1, y1 and x2, y2. So all I'm going to do now is write it as a matrix multiplication. So x2, y2 is, but this is the same thing as that, right? You realize because x1 cosine of theta minus y1 sine of theta and x1 sine of theta minus plus y1 cosine of theta. Okay? So hence, this is a rotation matrix. I'll call it volte-face R. This is the rotation matrix. About origin, you have to remember, about origin, counterclockwise by theta. You have to remember those things because it's derived under those assumptions. If I change those, this will change slightly. Okay? Is that fine? Everyone feels comfortable with that? No issues? Alright, good. So this is rotation by theta counterclockwise about it. Okay. Now the rotation matrix is actually an interesting matrix, and we'll have to deal with it a lot in this course. So we will kind of study it. It has some special properties as a matrix. It's not like any arbitrary matrix. It has some special properties. Number one, each row / column has a norm of 1, an L2 norm of 1, yani length of 1. Okay? How do you prove that? Cos square theta plus, how do you find norm of a vector xy? You say x square plus y square square root. That's the L2 norm. Okay? Which is just, you say distance formula or length, right? So in this case you have cosine theta and sine theta, so cos square theta plus sine square theta, you know by trigonometric identity is 1. So indeed the length of the first column and the length of the second column is 1. Cosine square theta plus sine square theta is 1. Sine square theta plus cosine square theta, that's again 1. It doesn't really matter whether you do it this way or that way, you will still get length of 1. So every row and every column. And since this is a general rotation matrix, so this holds true for any rotation matrix. Yani if you get a matrix where the row or the column does not have a norm of 1, you say it's not a rotation matrix. Okay? Another property. Each row or column is orthogonal to the other. What does orthogonal mean? Orthogonal means at 90 degrees, which means the dot product is 0, the inner product is 0. Okay? That again is easy to prove. How do you take dot product? If I want to take the dot product of these columns, how do you do that? You point by point multiply and add them, right? So you do cos theta times sine theta with a minus sign. That's the first part, and then sine theta times cos theta with a plus sign. So they indeed cancel out each other and you get 0. So the dot product is 0, and even if I do it that way, I'll get the same thing. So the rows are orthogonal to each other and the columns are orthogonal to each other. So the rotation matrix, so if that was not the case, it would not have been a rotation matrix. Okay? So we say that the rotation matrix is an orthonormal matrix. By orthonormal, we mean it has two properties. It is orthogonal and normal. Right? And then there is an additional property which holds true for any orthonormal matrix, and that is that the inverse of an orthonormal matrix is transpose. Now, this is actually quite easy to show for this case, even though it holds for any arbitrary orthonormal matrix in any dimensions, not just 2 dimensions. In any dimensions it holds true. But here it's actually quite easy to see. What would be the inverse of this matrix? Well, if I rotate it by 45 degrees, the inverse of that would be a rotation by minus 45 degrees. Okay? So, to figure out the inverse here, what I can do is I can find the matrix inverse and that would be okay. But I can just, instead of theta, put minus theta. And that would be the inverse of this matrix. And cosine of theta and cosine of minus theta is actually the same. Why is it same? Because cosine is an even function. It has a curve like this about the origin. So cosine of plus 90 degrees is the same as cosine of minus 90 degrees because it's an even function. And for sine, it's actually opposite. Sine of theta is equal to sine of minus theta is equal to minus sine of theta because it's an odd function. Okay? So if I put minus theta in here, the 2 cosine terms will not change. The 2 sine terms will change their angles. Change their sign. Right? So this negative sign will become positive, this positive sign will become negative, which is just the transpose of this matrix. Okay, the transpose means you switch rows and columns. So it's a nice property. I mean, if you feel uncomfortable, try proving it yourself. It's a nice property that if somebody gives me an orthonormal matrix and I need to find its inverse, I really don't need to do much. I can just flip the rows and columns and that's it. Okay. One thing that I've not written here, but I should mention, I don't know if it comes in some other slide or not, but I should mention here that I have said that every rotation matrix is necessarily orthonormal. Actually, it turns out that the converse of this is almost true all the time also. I say almost true, let me clarify that. Yani, if you give me an orthonormal matrix, it is a rotation. Okay? Yani, the converse also holds. Except for one case, the orthonormal matrix, if you talk about the determinant of that matrix, it will either be +1 or -1. If it's a +1, it's a rotation. If it's -1, there is a reflection involved there. Okay?
Rotation with the reflection.
Yes. I'll show this to you in just a moment. Okay. Alright. So what have I talked about so far? Scaling, which is like a diagonal matrix. Skew, which is like a triangular matrix. It's diagonal plus one more term. Skew along x, it's the term here. Skew along y, it's the term here. Shear, yeah. I said skew, but shear and skew actually mean the same thing. Okay, they are used interchangeably in the text. So shear along is a triangular matrix, either an upper triangular matrix or a lower triangular matrix. Okay, and I've talked about rotation, which is an orthonormal matrix. Okay, so let's talk about this system which we are doing. I mean, all the matrices that I've talked about are different values of ABCD here. Okay, and this is good for multiplicative type of transforms. Any multiplicative type of transform can be written as different ABCD here, right? So this is sufficient for scale, rotation, skew or shear. This is equal to that. But notice that we can't add a constant within the same format. Okay? If I wanted to say x is x plus 10, that type of transformation, I can't do it within the same format. Okay? So what I do is, why am I interested in that type of format? Because this transformation of adding something is actually a translation. Okay, if I am standing here and I just moved here, my coordinate added by that mass of the offset, right? So I mean, translations are important and you need to talk about that. Okay, so what we do is I could just add that here plus, let's say dx and dy as a translation, but that actually becomes unwieldy in certain ways. Okay, and so let me show you how we do this in transformations. What we do is instead of writing x in the inhomogeneous coordinates, we write it in homogeneous coordinates. So we extend it by 1. So it's x, y, 1, which means it's a P2 vector now. Okay, I just add one more to it, 1, a scale factor of 1. Okay? And then, because I have a 3 vector here, I make this matrix as 3 by 3 rather than 2 by 2. But I keep the last row as 0, 0, 1 because the last row is going to be multiplying by this and I don't need to change that. Okay? And so this C and F now actually becomes translation. Why? Because notice what will happen when I multiply this. I'll have A times X plus B times Y plus C because it's C times 1. And then I'll have, in the second row I'll have D times X plus E times Y plus F times 1 which is F. And so I got the translative component here within the same multiplicative framework. I just extended by 1 dimension. Okay? So this means now I can rotate, scale, skew and translate in the same equation just by changing the terms. Okay?
So can you tell me?
Sorry?
Can you tell me why you change it to 3 dimensions?
So I change it to 3 dimensions so that I can have an addition here. Through a multiplication I have an addition. And the addition is important. Why? Because translations are additions. Okay, if I move the image from here to here, that's a translation. It's just an addition of coordinates. So that's why additions are important. Now the question comes that why do it this way? Why not just add? I mean, why are we partial to multiplication? We like multiplication more than addition. I mean, why? Any idea?
Because we want to mix up the transformations and that's why we have to.
That's a very good point. The reason is that to do one complicated transformation, you might be doing a sequence of many different transformations, as we'll see soon. Okay? So you might say, okay, I want to rotate, and then I want to do a shear, and then I want to do a translation, and after that I want to do another rotation. Okay? If they are all matrix multiplications, I can just multiply those matrices together, and that would be simple. But if I have to do this, first multiply the 2 matrices together, then remember the third one is an addition, so add and then do another matrix multiplication, it becomes unwieldy. So it's the ease of coding and the ease of representation, the ease of mathematics that motivates this. Right? And the P2 space, the P2 representation, the homogeneous representation of vectors allows me to do that in a neat way. Yeah, there was a question.
Isn't this multiplication more computationally expensive than addition?
It turns out no, and let me come to that in a moment. Ask this question again in 10 minutes. Okay. Yeah. There was a question. Any other? Okay. Alright, so this is how we write a translation matrix then. A translation matrix is 1, 0, t, tx, 0, 1, ty, and 0, 0, 1. Because you can do this and multiply and see that x2 will just be x1 multiplies here, plus tx. And y2 will just come out to be y1 plus ty, which is a translation. Okay? And I can just extend the other matrices that I had, the 2 by 2 that I had with 0, 0, 1, 0, 0, 1, just to have them in the 3 by 3 format also. Okay? Just a word on notation. People write these things compactly in different ways. The textbook that we have that I showed you, Hartley and Zisserman text, they use this type of notation often. So to write this 3 by 3 compactly, they write it as identity 2 by 2 because this portion is identity 2 by 2. And then a vector t because that's tx, ty. And how do I know this t is 2 dimensional? Because this identity is 2 by 2. And then 0 transpose, 0 is a vector now because there are 2 zeros. So 2, 0, vector, transpose, and then just a scalar 1. This is just a compact way sometimes to write transformations. So it's nothing but notation so that I can write things more compact. Okay, I wanted to show you here so that if you see in a book, you don't get confused by them. Alright? So that's the transformation. So let's just review. This means this is a rotation matrix. I notice I extended it to a 3 by 3 matrix now, but it's the same thing because the extension is just by identity elements which don't impact anything. So this is a rotation matrix about origin, counterclockwise by theta. Okay. This is a scale matrix by Sx along the S x dimension and sy along the y dimension. If the scale factors are 1, that will be identity scaling, nothing will happen. If they are smaller than 1, shrinking will be happening. If they are larger than 1, expansion will be happening. Okay? This is translation. This is shear along the x direction. This is shear along the y direction. Okay? You'll get to practice these in your homework, sir.
Sir, so if you have a combination of two shears that will be equating to an expansion, so my question is, how does one decide to कौन सा अलग करना है? Do we
We're coming to that. So, in fact, the next slide is that. Okay. So that's concatenation of transformations. That's what you're asking for. How do we combine transformations? Okay. So suppose, so we call this concatenation or composition. It's not one simple basic transformation that I showed in the previous slide. It's something more complicated. Okay. So suppose, just as an example, suppose we first want to scale and then rotate. Okay. How would I do that? I already know how to do that, right? My original coordinate space is x. I first want to scale, so I multiply it by matrix S, which is actually a diagonal matrix. Okay, I write it as S just for notation here. So I get the scaling. The scaled space is x prime. Okay. Now I want to rotate, so I apply rotation R onto x prime, and that gets me the result of first scaling then rotation. But of course, by algebraic manipulation, I can substitute x instead of x prime. I can substitute s of x, because x prime is nothing but s of x, and then matrix multiplication is associated. So I can put the parenthesis any way I like. So I can call it Rs as one. R is a 3 by 3 matrix, S is a 3 by 3 matrix, so Rs is another 3 by 3 matrix. Okay? So that's what you were asking. It's a matrix that will do a combination. It's a single matrix, but it will do a combination of scaling and rotation altogether. Okay? A single 3 by 3 matrix will do that. And in fact, your question about computational complexity, isn't it more computationally complex? Well, 3 by 3 matrices multiply very fast together. When you want to apply it to the image, you have to apply on every pixel and kind of figure out where that pixel is going, right? So if I had two transformations, I first applied the first one on the image and then applied the second one on the image, I'm doing twice the work. Instead, what I'll do is because matrix multiplication is associative, I'll just first multiply the matrices together. I get one 3 by 3 matrix, and then it takes as much time to multiply it once or twice, right? No, it takes as much time to multiply the complicated matrix, the composed matrix on the image, or simple matrix on the image. Both are 3 by 3. So when I'm dealing with complicated transformations, I just first compose them together into a single transformation. This also tells me why treating translation separately would have been a problem.
Sir, we can translation with simple addition. We can 2 by 2 try करके x y से हमने add करना था, so apply भी नहीं करना था.
But the question is that, okay, suppose my composition was rotate, then translate, then scale. Okay, or let's say it was rotate, scale, like here, scale, rotate, then translate, then do a shear. Okay. Now I can compose the first two together, then add separately, then apply the third one. So I can't get it into a single matrix, which means I'll have to apply the first two on the image, which is 1 times the work, then translate, which is changing all the coordinates, and then do another. So I'm doing 3 times the work. If I'm combining it together, all those 4 transformations into a single matrix, that's only 1 times the work. Right? So you see why this notation is convenient of using homogeneous coordinates for these transformations, so that additions also become multiplications. Yeah.
When we multiply 2 by 2 matrices, this is not very fast as compared to a multiplication of figure combination. Is that converting actually beneficial compared to other translations of the original? Okay. So
No. Just do the math here, right? To do a 2 by 2 multiplication with 1 pixel requires 1 multiplication, 2nd multiplication, 3rd multiplication, 4th multiplication, 1 addition, 3 additions and 4 mults, right? Now applying this multiple times over let's say a 100 by 100 pixel image, which is a pretty small image, has like 10,000 pixels. So So doing this multiplication together is much less expensive than the application on the image itself, which is the slow part. So this is the same way you treat transformations, whether you are doing graphics, whether you are doing vision, whether you are doing virtual reality and so on. I mean, it's mostly standard way to treat transformations. Okay, the point I'm making here is that two transformations can be represented by a single transformation matrix. I'll call it RS. Okay, remember when I write it as M is equal to RS, S is applied first then R. Okay, because S was applied first and then R. Okay, so if you want to read a composition of transformations, you read it from like Urdu, right? From right to left, not from left to right. Okay. So it's important to read from right side to get the order of application. Why are we talking about order? Is order important?
Yes.
Okay, let me convince you that order is important. Okay, so I have an original image. I did a scaling by half. I did a rotation by 45 degrees, plus 45 degrees after that. Plus is going this way because this is the x-axis. So x-axis counterclockwise. Okay, let me do it the other way around. I did the rotation first and then did the scaling. They come out to be the same. So in this case, there is no difference. Okay. Is that good? Bad? Okay. Okay, but let me do some other type of transformation. Let me scale by half along x but not along y. Okay, and then rotate. Now let me switch this order. So if I rotate and then scale by half along x and not along y, I'll get this. And this definitely are not the same. Okay? So in general, A times B for matrices, you already knew this. Nothing, I just want to ingrain this on showing pictures, but you already knew this. In general, matrix multiplication is not commutative. Okay? However, in specific cases, this might hold true, like I showed you. In fact, in the case where Sx is equal to Sy, then the order of transformation does not matter. But if Sx and Sy were different in this case. In general, I mean, sometimes you might get a transformation where the order doesn't matter, but that's just a special case. In general, the order of transformation does matter. Alright? No real surprises here. That's how matrix algebra is supposed to work. Okay. Okay, let me talk about inverse transformations. So, the inverse of a transformation, what's the concept here? The inverse of a transformation should undo the effect of the original transformation. So if I take two steps this way, that's the transformation. The inverse of that would be two steps backwards. Okay? And what really works is simply taking the matrix inverse will work. You can say if A is the transformation, then multiply it with A inverse and you get identity. And identity means no transformation happened. Okay? Because the identity is one, I mean, it doesn't impact your point. Okay? So these are the inverse transforms. I already talked about this. For rotation, the sign just changes. The negative sign from here comes here. For scaling, it makes sense that the inverse transform would be, if I expanded by 2, now I should apply a transformation by half. Okay? So 1 over Sx, 1 over Sy is the inverse transformation. For translation, it's just the negative of the translation vector, because if I took 2 steps forward, I'll just take 2 steps backwards. And for shear, just the sign of the shear factor changes. Okay. And you can verify, these make logical sense, just because that has the effect of undoing the transformation, and you can verify that this is indeed the mathematical inverse of the matrix, just by multiplying this with the original and seeing that you get identity. Okay? And here's a useful mathematical identity also, that if you are inverting a combination of matrices, it turns out that it's the individual inverses multiplied in the reverse order. So AB whole inverse is B inverse A inverse. That's another identity that we're seeing in linear algebra. Okay? Right, let me pause here just for a moment. Is everything okay? This is mostly a review of things you already knew, right? Any questions? Okay, so then let us talk about special combinations of transformations, special categories of transformations that I can construct from these basic elements. Okay? To be able to talk about that, I'll talk about a topic which is actually a full-fledged topic in mathematics or in electrical engineering grad study, people study this, which is the topic of groups. You might have studied it in some course. Have you studied it in some course or not? Anyone who has? Okay, so let me just give you a preview of this because there's nothing to it really, at least at this time. Okay, a group is a special term that we use in math in linear systems. A group is a set G. So a group is a set. It is a set G together with an operation. I call it dot here. Okay. So a set and an operation, they combine to form a group that combines two elements of A and B to form another element A dot B if dot is the operator. Okay. For example, addition is applied. Addition as applied on the set of integers. So I might call it that that's a group. The group operator is addition, and the group is the set of integers. Okay. But to be called it a group, it must satisfy the following axioms. Okay. So there are some conditions for that addition and the set of integers to be called a group. Okay. So there are some axioms. What are the axioms? For all A comma B in the group, for all elements in that set, in our example integers, A dot B, the addition of them, the group operator of them, must also be in G. Okay? If it goes outside of G, then it's not a group. Okay? Yeah? Is that okay? So this is called the closure property. The group is closed. If I apply this operator to any elements of the group, the resulting answer will also be a member of that set. Okay? Alright. The second property that a group must hold for it to be called a group in this sense is associativity. Okay? Associativity means for all A, B, C in G, A dot B, then the dot of that with C should be equal to A dot B dot C. Okay? It holds for addition, for example. The addition of integers is holds. So this is called the associativity property. Then there is the property of identity. There must exist an element E within the set G, within your set of elements of that group, such that A dot E is equal to E dot A, which is A. Yani there exists an element that when you apply the group operator to it with some element, some other element of the set, that other element will not change. In the example of addition of integers, this identity is 0. So 0 exists in the set of integers. So that means that addition as applied to the set of integers is a group. If I said addition applied to the set of whole numbers not including 0, then it wouldn't be a group because the other properties would be true but identity property would not be there. Okay? And then finally the last property is inverse. For each A in G, in our example for each integer, there should also exist another element B such that A dot B gives identity. In the set of integers, if A is a positive number, B will be the same number with a negative sign. So that 2 plus a minus 2 would be a 0. Okay? So the set of positive integers, addition would not form a group over the set of positive integers only, because the other element will not exist to make it identity. But addition would be a group over the set of odd integers. Okay. Alright? This is just definition of group, and this leads to a whole branch of mathematics called group theory.
So can there be multiple operations?
That would be another group.
That would be another group.
Yeah, I say to define a group, I have to define the set and I have to define the operator.
Operations, can there be two operations there?
So that would be another group. Like addition over set of integers is one group and subtraction over the set of integers is another.
Is there going to be a group with addition and subtraction both?
Well, that's just two groups.
Two different groups.
Yeah. Okay? Alright. The reason I talked about groups is that I'm going to talk about transformations that we just discussed as groups. And this gives us a very interesting picture to talk about transformations. Okay? So the simplest transformation, the first one that I'll talk about is a translation. Okay, and I'm writing it in different notations so that you get comfortable with notation also, but it's just I2 times 2 pipe. Pipe means concatenation of column. So pipe T, I wrote it as a 2 by 3 matrix just because the last one was 0, 0, 1, so if I drop the homogeneous notation for translation, it doesn't really matter. Okay, and then, so this is really these equations. I mean, if I expand this, it's really this, x plus tx and y plus ty. Okay, so I'll call it the translation group. The operator here is translation. Okay, I mean the operator here is this T in this form of the matrix. That's how you apply your transformation. So this equation is the operator, and the set here is the set of all possible vectors T, because any one of them is a translation. So my claim is that translation is a group. Okay. Translation on the set of all possibilities is a group. Let's go back to group axioms and verify that they all hold true. For all A, B in G, and for any two translation vectors, you can come up with the result of that is a combined translation which is also in that group. If I take 2 steps this way and then I take 1 step this way, that really is a translation which is this way. Okay, so I'm still within that same space. The result is within that same space. Associativity. If I take 2 steps this way, then 1 step this way, I could really have taken 1 step this way and then 2 steps. That's commutative. Sorry, commutatively also. Let me do associativity, right? How would I do that? I'll take 2 steps this way, and then 1 step that way, and then I will take 2 more steps this way. Okay, so I first did those translations and then did the second one. Well, it would look exactly the same if I just changed the parentheses and did this again. I will say, this is my first translation, I'm done, and then I will do these 2, and I end up at the same place. Okay, that was not so bad. Okay. So associativity obviously holds for translation because the basic operation in there is just addition, and we know that associativity holds for addition. I didn't have to do that fancy dance to do that. Identity. Of course, if T is 0, 0, that's the identity element. And inverse, of course, for every translation, Tx, Ty, minus Tx, minus Ty is the inverse of that. So translations form a group, which means by doing as many translations as you want, you can never get to something which is not a translation.
So the inverse property can be, it's not that inverted, can be elaborate on that?
The inverse property is that the inverse should exist, right? And for a translation, so multiple ways to see that. First, if I do 2 steps this way, the inverse of that is that I take 2 steps backwards. If the translation vector is Tx, Ty, then minus Tx, Ty gives you the inverse. Or you could just take the matrix and invert it, and yes, the matrix inverse exists because this is a non-singular, this is not a singular matrix. All the elements are 1, so you can surely invert any matrix of this form. So it's a full rank matrix, it's a whatever. Okay. So the inverse must exist. There are many ways to see that. Okay, that means translations form the group, which means by a sequence of pure translations, no matter how many you do, the result should be describable by a single translation, because that also lies within the group. Or another way to say that is, by doing no matter how many translations you do, like 1,000 of them, you can never get the effect of a rotation. Right? Because the net effect would also be in that group.
So the groups can overlap, is that the translation का group जो है वो rotation के group से overlap नहीं करेगा?
No, I mean groups do overlap, but not in this case. I'm saying the result of 1,000 translations would still be a single translation, because when I combine 2 translations, it should give me 1 translation, which is the result of A dot B should also be in that group. and then I do one more, so that result should also be in that group. So ultimately, the concatenation of 1,000 translations should also be a translation. I can never get outside the space of translations, outside the group of translations, just by doing translations, because translation is a group. I'm saying, so rotation is something different from translation. So if it was not a group, maybe I could have gone outside it, and outside it lies rotational engine. So I'm saying that's not possible because it's a group. So no matter how many translations you do, you cannot get an effect of a rotation on it. Okay. So having said that, let's talk about the next level of group, which is I'm defining it as a rigid body transformation, which is a rotation concatenated with a translation. Yani the first 2 by 2 part of the matrix is cos theta minus sin theta cos theta, and then you have a translation vector with it also, tx ty. Okay, we call it rigid body. So if I multiply this together, it comes out to be this, right? This is the rotating part, and this is the translating part. Okay. The reason we call it rigid body as a special category is that this is like, if I do something on paper, then I can rotate it and I can move that paper, but I can't stretch it. I'm not allowed to stretch it. There is no non-rigid deformation allowed in this. So it's a rigid body transformation. Okay? And my claim is rigid body transformations also form a group. And you can go over your group axioms and convince yourself of that. I mean, I'm just stating that they also form a group. In fact, in this group, that entire group is contained within this group, right? Because in the rigid body transformation, I can choose any R and T, and if I choose R to be identity, then it's a pure translation. So the translation group is a subgroup of the rigid body transformation. It's like a hierarchy. The rigid body transformation encompasses a lot of transformations. Some of them are pure translations. Okay? So let's talk about the next one, which we call a similarity. A similarity is a scale factor multiplied by the rotation, but it's one scale factor. One scalar multiplication multiplied by the rotation times the translation. Okay? I mean, concatenated with the translation. So notice I have Sx here, Sy here, Sx here, Sy here. Okay? It's just scale. Which means what? It's so this particular category, you can rotate, you can translate, but you can also expand equally on both axes. You can change the size equally on both axes. Yani you can zoom in or zoom out, but not do like a squish, unequal scaling. Okay, so this category is called similarity, and similarity again you can see entirely contains rigid body within it, because S is, if I choose S to be 1, then it's just a rigid body, and if I choose R to be identity, it's just a translation. So this is indeed a hierarchy of transformations. Okay. So each higher group completely contains the lower group. Okay. So one last group that I'll talk about and end here on this slide is the affine group. Now this is the general 2 by 3 linear transformation. By 2 by 3 I mean the third row can be 0, 0, 1 if you are writing it as a 3 by 3 matrix, it doesn't really matter. So this is the general A1x plus A2y plus A3, A4x plus A5y plus A6. Now if those A1, A2 and A4, A5 form an orthonormal matrix, then it would be a rigid body then that portion would be a pure rotation. So it will become a rigid body transform. If this and this form a scale factor of an orthonormal matrix, then it's a similarity. But in general, they don't have to follow that constraint, so it could be any 4 numbers, and these could be any 2 numbers. So that particular group, it also forms a group, and that particular group is called the affine group. And in the affine group, all of these are contained within them: rotation, scaling, shear, translation, or any combination thereof. They are all contained within them. Okay? So an affine transformation can, for example, transform this picture into a picture like this. That would be some choice of parameters of affine transformation. Okay? And I have a statement here that I have not proved. An affine transformation preserves parallel lines. Yani parallelity of lines will not change. If there were two lines in the image which were parallel before you did affine transformation, no matter what type of affine transformation you apply, those two lines will remain parallel after affine transformation. Now shading is also an affine transformation, and you realize that the box shifts like this, parallelity is preserved. Rotation is also an affine transformation, and you realize that parallelity is preserved. In fact, each of these groups has some things that are preserved. Okay? In translation, what is preserved? What doesn't change in translation? What property doesn't change in translation? Sorry? Lengths and angles. They remain same. Okay? In rotation, lengths remain same. In similarity,
The ratio is there. The ratio between the lengths.
yes, the ratio between the lengths remains same, and in fact, any angles between two lines, they also remain the same. Okay? And in affine, none of those are guaranteed to remain the same, but parallelity of lines remains. It holds. Parallelity will remain the same. Now, I have not proven this because that's in your homework. So you will do it.
सर जो थर्ड जो था सिमिलरिटी वाला
Yeah.
उसमें जो हो गई रोटेशन हो गई तो रोटेशन और स्केलिंग में ऊपर दोनों चीज़ें हो गई तो हमारा एंगल और साइड दोनों
No, sorry, I think I made a mistake. On rotation also angles are preserved. Yani angles, I'm saying angle between two lines. If there were two lines which are at 90 degrees to each other, after rotation they will remain at 90 degrees to each other. So rotation also preserves angles. Affine or skew does not preserve angles. Yeah. Okay, very good question. You can guess from here that there will be a group after affine that we will talk about, which was the next slide, but we are out of time. We'll tell that tomorrow. But there will be a group after affine which will, because every group distorts some of the properties of the previous group, so there will be a group which will distort the parallelity of lines also. Okay? And actually that's the last group we will talk about, which is called the projective. Yes?
So is having the LA tutorial on Friday a possibility instead of today?
So far, no. It might become a possibility later. I might have to travel on Friday, but I might not, so it might become a possibility. Are there other takers? Yes. I think the LA tutorial right now today is very important because you have the homework due today, and to do that homework you need the LA part.
Due today.
Yeah. No, the homework is not due today. The homework is assigned today. So if I delay the tutorial till Friday, it means you lose 2 days on the yeah. Yeah, this particular homework is probably the only one where you have to do it with a pen and a paper. You could do it on MATLAB if you want to, but you have to submit results in written form as a typed document or as a handwritten document. The other homeworks will not be like that. Okay. Anything else? Any questions? Further questions? Yeah.
Which are talking about which will not preserve parallel lines.
Yeah. Yeah. You're right. Yeah.
This one is a general.
This is a general 2 by 3. So you are right that the next one will necessarily be a 3 by 3 transformation, not a 2 by 3, because I've covered anything that I could have done with a 2 by 3 transformation here. Yeah. You're right. Any other questions? Okay. Thank you. We're done.